Yeah, okay. So a long break happened, and by long I mean 1 day. And yeah, so we previously solved the order in example 7 is you know an order relation, and that so it will actually follow from the fact that every dictionary order relation is a order relation, and that's because this is exactly a dictionary order. So essentially, and I was avoiding the proof of the dictionary order being an order relation because I kind of showed it through an example. It's the same thing. So yeah, let's go on to question 10 now, right? Yeah. So question 10 talks about example 9, which is, yeah, x upon x minus x squared. Sorry, 1 minus x squared or x minus x squared? 1 minus x squared, and we have to show that it's order preserving. Okay. Also known as isomorphism. All right. So, okay, this is a function from R to R. Is it? It's not from R to R. So what is it exactly? Oh, minus 1. Minus. Yeah. Yeah. Okay, so how do you show that? Well, we take any two real numbers, and so essentially we have to show a less than, to call it a and b, if and only if f of a, f of b, correct? And of course, f must be a bijection. So how do you show it's a bijection? Well, let's see. Take any real number. Let's take c, and so c is equal to x minus x upon 1 minus x squared. C minus cx squared is equal to x. Cx squared minus x minus c is equal to 0. Correct? Yeah. So I think we only get, yeah, we have to show that we only get one root in minus 1 to 1, and that is the unique inverse that leads us to the real number. Okay. Yeah, should be fine. I hope you can hear me. Yeah, sorry, I just took a break. So C, no, X is equal to, what do we get? We get, yeah, 1 plus minus 1 plus 4ac. So 1 plus, what is it? 4ac. So C into C into 4. So yeah, all by 2. 2a, 2c. Yeah. And which of these is more than 1? So because c square is always greater than 0, uh, and x is, okay, x has to be between minus 1 and 1. So, okay, so I didn't actually have to think that hard. Just let's see. So this term, 1 plus 4 c square, is definitely under pretty much under all circumstances greater than 2c, correct? So yeah, just use that here. It's greater than 2c, so the whole thing will be greater than 1 if we take the plus term. So that means we can only take the minus term. And let's check it. Yeah, we can only take the minus term, and if you take the reciprocal and try to, perform your conjugate algebra, you'll get exactly the function in the next part. So yeah, we have to take the minus term. So I'm just going to remove it here, minus term. Yeah. So this is a unique function, and we're getting, so for all real numbers, we're getting, for all real numbers C, we're getting an x such that f of x is equal to C, right? Okay, so it's surjective. Now, how do you show it's 1, 1? Right. To show it's 1, 1, let's see, y upon 1 minus y squared is equal to x upon 1 minus x squared. Uh, yx squared is equal to x minus xy squared. Can we do something about that here? Let's see. And let's see, y minus x minus xy, yeah, y minus x, okay, is equal to 0. That means we'll prove it later, but with this, what do we get? Yeah, so we'll prove it later in the next section, but one of them has to be 0. So if, and this, can this be 0? Well, x and y are both less than 1. The model, because of that, this is actually never going to be 0. So this means that this is 0, which means y is equal to x, which means it's injective. Okay, so it's a bijective function. Now what? Now we need to show that the order is preserved. So how do we show that? Let's see. All right. So let y greater than x. We have to show y upon 1 minus y squared is greater than x upon 1 minus x squared. Also, yeah, keep in mind that the graph is there to help you visualize it. So, okay. Now, because the modulus of x and y are both less than 1, this is a positive term, so we can multiply it on both sides with it. I really shouldn't be proving it with algebra, but I might as well. And the next section covers it. So there's that. Anyway, so because they're both positive, we can multiply. Okay. Now what does that mean? That means same thing. All right. So is this always greater than 0? Yes. So we can cancel it out. There's a proof. This will be proven later. What does that mean? That means this is greater than 0, which means, yeah, what did I just show? Oh, okay, yeah. So I just have to show its equivalent, right? Okay. So I just prove this direction. Now I have to prove this direction. So let's see. If y minus x is greater than 0, I can multiply it with a non-negative term and get the same inequality. Non, it has to be greater than 0, not non-negative. Sorry about that. Yeah, and I can expand it and cancellation law. So we'll prove all of that in the next section. This follows, and this also follows. I'm just dividing it by 1 minus x squared into 1 minus y squared. So far it's all equivalent. Equivalent. Yeah. So that's how you directly algebraically prove it. Oh, my face. Whatever. Yeah. Okay. So, yep, that proves its isomorphism essentially. Now let's show that the inverse function is so let's show that this function is an a left and a right inverse. So what's the function? 2y upon, yeah, 1 plus 1 plus 4y squared. Ah, yeah, it's using a lot of terms that were defined later. So it's fine because they're kind of independent questions, but essentially we're using high school math, so it works out. Anyways, we have to show that this is left inverse. So is that quadratic of a violet proof? Almost. Okay, so is it well defined on the entirety of R? Let's just check that. Well, when is it going to be 0? That's when it's not going to be well defined. And since y is squared here, it's never going to turn to 0, right? Because this is greater than 1 for sure, for all. In fact, greater than 2y, but, great 2 mod y. Yeah. Oh, yeah, the C was mod there. So I should have written that there. Oh, I see. Oh, yeah, there were some cases of C being positive and negative, but they all work out. Yeah, I have to see. Or I won't see actually. It's fine. Okay, so because of that, it's defined on the entirety of R. So that's a check. Now Now we have to show that this composed with the function x upon 1 minus x square is the identity function. So to show that, well, we can just put it in here, I guess. That's one way. Or yeah, we can try algebraically finding the inverse function. Do I want to do the f of x is equal to 1 minus x square. So from all the algebra, we'll derive that x is precisely equal to 2 f of x upon 1 plus 1 plus 4y. So this we're arriving at from the quadratic formula I just used earlier. Now, what does that mean? Yep. And this is equal to precisely GOF of x. So yeah, it's indeed the identity function. And what does that mean? That means since f is bijective and it's both a left and a right inverse, why is it a left and a right inverse? So for the right inverse, we'll have to check FOG, right? So the algebra works both ways. I'm just going to say that. So FOG of x is equal to x. You just have to try it. Yeah. So what does that mean? FOG and GOF of x are both equal to x. So we got a left and a right inverse. Therefore, we got a bijection, and that's heading backwards. And essentially, what that means is minus 1 comma 1 is isomorphic to R in the order sense, pretty much. Yeah. Okay. Show that an element of an order set has one, at most one, and at most. Okay. Subset has at most one smallest element. Okay. So let's see. First, we have to take a subset of. We have to take an element of an ordered set. Okay. So let X be an ordered set. Let X be a member of it. Now let A1 and A2 be the immediate predecessor of X. This is bad notation because of other things, but I'm just going to use it for the time being. Now, so what does that mean? Now that means A1 is less than X, right? It can't be equal to X. A2 is less than X. And for all B belongs to X such that B is less than X, B is it's immediate, right? Oh, how am I able to use that? Let's see. I'll use the definition first and then I'll show why I could use it from the definition that the book gave. So B is going to be less than equal to A1, comma, both, right? Okay. Now we take the set. Okay, we take the set X, sorry, Y is greater than A1 or A2 and greater than X, right? So this set is supposed to be empty, right? By the definition of immediate successor. So what does that mean? That means, yeah, it's a triangle inequality business. Let's see. So if B is less than X, B is less than X, and B is not less than equal to A1, A2, then B will be greater than A1, which will contradict the fact that this is empty and therefore contradict that A1 and A2 are the immediate predecessors. So that's how I can state this. So this is in a way a theorem about immediate predecessors, right? So essentially, this is an equivalent definition, and I'm going to use this now. Now that we have this, uh, yeah, so B is less than equal to A1 and A2. But since A1 and A2 are both less than X, what do we get here? We get A2 is less than equal to A1 and A1 is less than equal to A2. That's fine, right? I'm just using B as A1 and A2 and B as A2 and A1. So I'm getting both of these. But what does this mean? This means A1 equals to A2 or A1 less than A2 less than A1 and A1 equals to A2 or A1 less than A2. And by totality, since only one of these cases can occur, this case must occur. Otherwise, we're contradicting totality and the fact that X's are not at set. So what does that mean? That means A1 is equal to A2, which shows the uniqueness of the predecessor. And by a similar argument, you just I'm just going to, it's the exact same thing. I'm not even thinking much. I'm pretty sure this is correct. So yeah, I have not put a single amount of thought to it. I am pretty darn sure this is correct. But yeah, that's how you show that there's a at most one. So yeah, if you want to show that there's at most one of anything, showing that it's unique is enough. Because if it doesn't exist, we don't really care. We don't care about that case. So if it does exist, any two of them are going to be equal. That works. That's one technique at least. Okay, now how do we show it for the largest element? So let X be an ordered set and let A be a subset of it. And let A1, A2 be the smallest element of A. So what does that mean? I'm just going to call it small. I don't care. Okay, so what does that mean? That means for all X and A is less than equal to X, right? That's what it means to be the smallest element. Yeah. Okay. So given that we already have the quantifier, I don't think we need this anymore. Yep, it's simple actually. So since it applies for all X and A, and A1 and A2 by definition are NA because that's what it means to be the smallest element, A1 is less than equal to A2 and A2 is less than equal to A1, which implies A1 is equal to A2. Also, A1 greater than A2 and A2 greater than A1 is not a thing, right? That just means it's not a totally ordered set. So we forget about this. It's the greater than equal to that allows us to make arguments. And you'll see this trick throughout analysis, and it's very similar to how you show subsets implies equality. It's almost the same thing. So it's an extension of that idea. And I'm not showing it for largest. It's just, you just flip it and you put it. Yeah. Okay. So, okay, we have an order. We have a dictionary order on Z cross Z. Z plus cross, yeah, Z plus cross Z. So what's the dictionary order here? We have, I just gave an idea, 0, comma 0. Then are we going which way? Hang on. Yeah, so it's 0, comma 0, then 0, comma 1, then 0, comma 2, and then at some point you get 1, comma 0, right, and so on. That's the dictionary order. And then at some point you get 2, comma 0, and so on. There's a bunch of stuff in between. Yeah, that's the dictionary order. And the second order is essentially second and third order. What are they? Yeah, so So first we're checking whether they're on the same line or not. So this is the origin, right? And so first we're starting with y and x are both 0, but then we're going to the next point along the line y is equal to x, or y is equal to minus x, right? We're going along the line and we're going above the y coordinate, and then we go to the next line, y is equal to plus minus x plus 1, and so on. So we're going this way. And in the other case, we're going this way, right? So what did the question want to ask about? So let's work with some properties. Okay, so in the y plus x order, so it's going this way. Every single element has a previous element. Every single element has a predecessor, right? Why is that? So you take any natural number, we'll go along the line and we'll have a previous one. And there's no notion of getting to infinity here, right? That's one thing. So in this order, no predecessors. Sorry, all predecessors. All right, that's one property. And in y minus x, right, we go this way. 0, comma 0 has no predecessor, right? What about any other natural number? Let's see here. Let's say 1, comma 0. That also has no predecessor. Yeah. So there are at least countably many elements with no predecessor. We'll talk about countably too. It just means that think of countably as the infinitude of the integers. We'll get to the infinitude of the reals and then discuss more. But yeah, we'll have countably many that have no predecessor. And a similar thing with the dictionary order. Why? Because 1, comma 0 has no predecessor. 0, comma 0 has the smallest element. We'll get to that too. So in the dictionary order, there are also countably many elements with no predecessor. Okay. Now, what about the smallest element? So in this order, y plus x, there is a smallest element, and that's 0, comma 0, right? And in the dictionary order as well, 0, comma 0 is the smallest element. But in y minus x, there is no smallest element. And why is that? That's because you take any natural number, you can always go below a line and go ahead. So you can just actually go ahead in the line that alone is there. Yeah, you just go along in the line. Take any element of z cross z plus cross z plus, and you go along the line in this order, and there is always going to be an element that's lower. And yeah, if it happens to be in the base, then you just go to the next line. So yeah, there's no smallest element. So what does that mean? That means this has all the elements have a predecessor. That means it cannot have the same order type as these two, because if there was such an order, such a bijective mapping, then let's say this thing was mapped. Let's say we took an element that doesn't have a predecessor and we mapped it to an element here. Now here there isn't a predecessor, so we choose that, and we'll get a contradiction, because since there's another element below it that's so there's another element that's below above A and below f of B, above f of A and above f of B, that must be there. But according to this, it isn't there. So that's the contradiction. So because of that, the y plus x order is different from both of them. And because of the smallest element, the y minus x is different from both of them. And because the dictionary order is different from y plus x and from y minus x, it's different from both of them. So all three have a different order type. And yeah, you can study various properties about it. I think there are more properties, but I think that's all the question really wanted us to explore, and I'm not too interested. So yeah, let's go to the next one. Okay. GLB or LUB implies GLB, one of them. The equivalence will follow from the next question. Okay. Oh, okay. Yeah. So has the least upper bound property. Okay. So let A be an ordered set, and we want to show any B that's a subset of A has the greatest lower bound property. Uh, any arbitrary. So if we show that any arbitrary subset B of A has a greatest lower bound, we're done, right? Because B is arbitrary. So that's what we have to do. Okay. Now, hmm, okay. So let's take the set of all elements X such that for all B and B, X is you want greatest lower bound, right? Yeah. X is greater than equal to B. Yeah. This is a set X. All right. And belongs to it. So this is a set, and because X belongs to it, it's exists by comprehension, but don't think about it. You do need to include this X belongs. Anyways, so yeah. Now, because this is a subset of A, right, it's going to have the least upper bound, right? So let the least upper bound of this set be Y, all right? I'm going to call it N. I'm going to call this S, right? Now, if we show that this Y is the greatest lower, hang on, what? It has the least upper bound, so it's the infimum, sure. Oh, sorry, that's supremum, yeah. Okay. Yeah, so if we show that this Y is also the infimum of B, then we're done, basically. Yeah. Mm-hmm. So to visualize, what I'm trying to do here is since the set of all elements, greatest lower bound. Hmm. Yeah. Since the set of all elements less than equal to B, so it's going to be something like this, right? A part of A has the least upper bound. If we, yeah, no, yeah, has the least upper bound, we'll find it here. And if this element happens to be the greatest lower bound of B, then we're done. That's kind of what I want to do. All right. So how do we do that? Let's see. So since Y is the supremum of S, that means Y belongs to S, right? No, it doesn't. Sorry. Y is greater than equal to X for all X and S, right? And by the transitive property, since, yeah, I have to think a bit. Okay, took too long of a break. Yeah, so this is the set of all lower bounds of B, and Y is the least upper bound of the set. And yeah, now we have to show that this Y is the least, no, greatest lower bound of B. That's what our goal is, right? So first you have to show that Y is a lower bound of B, all right? So let Y not be a lower bound of B. That means there exists B and B such that Y is greater than B. That's the only way it's possible, right? Okay. What does that mean? That means that since B is so is B going to be a part of the set or something like that? Let's see. Hmm. We have to reach a contradiction here. B is going to be hmm, so is B an upper bound for this set now? This B. Uh, since B is in B and all of the X are less than that, okay, so first we'll show that for all, it's easy to show that for all B and B, B is an upper bound of X, of S, right? And why is that? That's because, B is greater than equal to X for all. Yeah, that's what it means to be an upper bound. So B is an upper bound and B is less than Y. So Y is not the least upper bound anymore. And that's a problem. So that's a contradiction. And because of that, Y has to be by totality, total order, Y is less than equal to B. So what does that mean? That means it's a lower bound of the set B, right? Since this is not the case, we have to negate the entire statement, and that means for all B and B, Y is less than equal to B, right? Okay. Given this, Y is a lower bound of B. Now we have to show it's the greatest lower bound. Hmm. Well, yeah, if let's say X less than Y is sorry, X greater than Y is the greatest lower bound for B, then it will contradict the fact that Y is the it will contradict the fact that Y is an upper bound of the set S because hang on, I have to think. Let's see. So if X is greater than Y, right, we have to show it's the greatest lower bound now, right? And for all B and B, X is less than equal to B, right? So what does this? This means, uh, okay, if X is a lower bound, then has to be less than equal to Y. Yeah, there you go. So if this is the case, then X has to be less than equal to Y by Y being the supremum, and it's contradicting X greater than Y. So because of that, Y has to be the greatest lower bound. So what does that mean? That means for an arbitrary set B, we have found the greatest lower bound. And that's it. Yeah. From the least upper bound property. So GLB implies LUB implies GLB. Okay, so there's potentially a lot to edit because I may have made a lot of mistakes. We're solving question 14 again, just in case. First part is correct, so I'll put that in. Just okay, fine. I'll do it again. Question 14. Don't dry up. Come on. Yeah, hang on. I'll be back. Yeah, let's just do question 14 again. Cool. Yeah, let's do it again. Mm-hmm. Okay. So essentially, comma B belongs to C implies B comma A belongs to D, and this implies this is symmetry. Okay. So if C is equal to D, this implies this directly, and this implies Hmm. Okay, so let B D have A comma B, right? Must C have B comma A in it? That's the question. So let B comma A not B and C. Yeah, I'm gonna have to assume that it's equivalent. Okay, so given that it's defined that way, it has to be if and only if there's no other way around it. Fine. So I was essentially confused on what the question meant by A comma B belonging to, so whether it's equivalent or not. So I'm taking it as equivalent. I don't think the one-way implication alone makes sense. So I'm going to take this to be true. And given this, if C is symmetric, it's pretty obvious that D is equal to C, because if A and if it's symmetric, then by symmetry it implies this, which is if and only if belongs to C belongs to C. Yeah, and if and only if A comma B belongs to B. And this would be implied by equal by equivalence. So this is implied by symmetry, and this is implied by equivalence. In fact, this is implied by symmetry. But yeah, because of that, they all turn out to be equivalent. So through this link, you'll get this link. Like, yeah, they're both the same link. Okay. Question 14b part. We have to show that it's an order relation. All right. So it's non-reflexive. So A comma B belongs to C implies A is not equal to B, right? Now A comma B belongs to C implies B comma A belongs to B, right? And take any C comma D in D, it implies D comma C is in C. And since it's in C, C and D are not equal, therefore it's non-reflexive. Fine. Yeah. And what about transitivity? Yeah, you use the same prop. So essentially, you take C comma D, A comma C, and you go to the other flipped world and use transitivity there and then flip it back. So it's fine. And for total order, same thing, you just flip it. So the sets are order relation is preserved. I'm not doing it here. All right. Prove the converse of the theorem. So yeah, it directly follows. Let's see. If A is LUB, we have to show, sorry, GLB, we have to show that A has the LUB property, right? So if A is LUB, then so A and C are the D and, okay, I'm just going to put the D here, yeah. C and D are the original sets. And if C is having the GLB, then D will have the LUB because every single sign is flipped essentially, right? So essentially all lower bounds will turn to all upper bounds, and this turns to that. Yeah. So because of that, you can verify that C being a GLB implies D is an LUB. Now, LUB implies GLB was just proved. And of course, D is an order. That's what we had to show earlier. I am not sure what the first part was for. I think it was just an exercise. Anyways, since D is a GLB, that implies C is a GLB, LUB. So we are done with the question. And yeah, the whole point was that you can come backwards from it too. C can be defined using D this way, once D is defined, because if C is equal to A comma B, B comma A belongs to D, right? That what does that mean? That means A comma B belongs to C by definition. So we're preserving the original set essentially, since this is equivalent to this. All right, let's go question 15. All right, so keep in mind that any arbitrary subset of the real line does not have to have the least upper bound property because the set of rationals don't have the property, right? That's a good example. So what we mean to say is that every subset will have a least upper bound, not the property, right? Okay, so in a way, the reason they didn't tackle this one or any order preserving bijection, so it can be any A comma B essentially. They didn't tackle the open intervals because it's isomorphic to the real numbers. I'll just say that there is an isomorphism. So and it is pretty easy to show that if two order relations are isomorphic, then the property is preserved. How do you show that? Uh, yeah, you just go from the first order to the second order essentially. So because of that, I am going to use without proof that this has the least upper bound property, right? So now we just have a couple of cases to work with. One, this one. So 0 is included now and 1 is not. Now, any subset of this interval, now there are two cases. One, 0 is included in the subset and 0 isn't included in the subset. And if 0 is included in the subset, then 0 will have let's see. Yeah, so 0 will be the least upper bound. Greatest lower bound. And why is that? That's because 0 is by definition less than equal to x for all x belongs to this set, right? Okay. And what about 1? 1, so similarly, 0 comma 1 has the LUB property and the GLB property by the same argument. Now, by the previous theorem, since this has the GLB property, it has the LUB property. Yeah, I am. So essentially, the main trick is just isolating the 0 comma 1 interval. And then we just got a bunch of cases, right? If it's included or not included. So to summarize, 0 comma 1 is isomorphic to the real line, right? And because of that, this has the least upper bound property because the real line does. And then we take any, for this set, we take any arbitrary subset. If it has 0, then we get a least upper bound. If it doesn't have 0, then we have essentially 0 comma 1. So since it's a subset of 0 comma 1 and 0 comma 1 has the least upper bound property, it will have so. And we've got a least upper bound with including 0. And yeah, we include or not, don't include 1 and 0 and we'll get the property. Yeah. And that concludes the exercises for chapter 3, section 3. Okay, so that's all question 15b. Sorry, I wrote this down while explaining, but I didn't wear my headphones, so it was recording the wrong way. And yeah, so openness, I'll talk about that later, will be represented by curved lines. And essentially that's, it's like the open interval. And polygon rigid lines will be represented by, will represent closeness. So in this case, this is closed interval 0 comma 1 cross 0 comma 1. This is the first one, which is, I'll just write it down, 0 comma 1 open cross 0 comma 1 closed. And this represents 0 comma 1 closed cross 0 comma 1 open, right? And we have to check the least upper bound property for all of these. So I think here there's no counterexample, and I'll try to prove it. And of course, the dictionary order goes this way from down to up. But because an actual dictionary goes downwards, I was more used to writing it this way. And proof-wise, it makes no difference. But yeah, ultimately, I should try shifting to the correct one. Yeah. So it's going this way, right? And you take any subset, right? Anything at all. What's going to happen? You're going to take the least upper bound. That's what we need. So here is going to be a point. Is it always going to be a point? Yeah. So I think there's no problem with the ordered square because it looks pretty close to like a subset of the it's a subset of the real line. So, but yeah, let's not use that. Hmm. Wait. Okay. So what if we take a circle? A circle in this would have an optimal point here, right? And that would be the least upper bound pretty much. So you just go to the left. Okay. Anything weird like hmm, never reaching there. Yeah. In any weird case, what will end up happening is hmm. Okay. Let's consider this case. So like a triangle, right? A triangle without the endpoint, so it's open in a sense in the square, right? Let's see what happens here. So the endpoint is not included here. Is that going to be the least upper bound, or is it going to be this instead? Hmm. Yeah, there are a lot of things to consider. Hmm. Yeah. Yeah. Okay. So the circle is going to have this as the upper bound if it's open, and it's going to have this if it's closed. Same thing with the triangle and basically any shape you can think of. Now we have to check at the boundary point, right? For a proof, uh, yeah, I don't know about a proof, honestly. I don't think I can prove it. And I think it is tackled later, but yeah. So currently, I don't think I can prove it yet, anything about it. Okay, so now what? Now, let's say we have an open interval, right? So it's defined in, let's say 0, comma 1 cross 0, comma a, right? So what's going to be the yeah, it's any open thing at all, it's going to just go to the next element basically. Yeah, so it's going to be some 0, comma a basically. That's going to be the point. This is the point notation. So, if you want, we can write it this way. But yeah, so at least intuitively, I cannot prove it, but 0, comma 1, the closed square seems to have the least upper bound property. Okay, now what about this one? So, hmm, let's take that same triangle here. We might encounter a problem here now. So, okay, we'll definitely encounter it at the boundary here, right? Yeah, it will be a problem because essentially we're looking for the point right above it, but we can't. Yeah, so the triangle will be a problem because there's no such thing as a, 1, comma something. We can't have a 1, comma something, even though that's what it wants to get to. So with the same triangle that we could get to the next point of, we can't get the highest point here. So if you want a concrete example, you'll take the open disk and at one it's open and at the remaining points it's closed, right? Open square, kind of. I'll write a formal one later. Let's see. So, like, yeah, I just restrict it to maybe, zero point 0.5, comma zero point 0.5. That, and then you'll get the square. And you won't have any upper bound, right? Yeah. For this one, see, hmm, can we extend the triangle this way? Let's see. Hmm. If we have any closed interval here, I mean, if it's closed, then we can just, get the same point. So, hmm, okay. So if we take a triangle that's, open at the boundary that way, what will be the supremum? Okay, let's try another. So, yeah, okay. And maybe open at this point too. Let's see. It seems this might have the LUB property. I'm not entirely sure because at the very next point, whatever we take, it seems we can go to the 0 point. Hmm. But yeah, maybe not. Let's just. Uh, what if it's open here? Then what? I'm not sure. I'll leave it for later, maybe. So I'll try to discuss this after we cover section 24, maybe. So what I can definitely conclude is that this set is not having the least upper bound property. Anything else? So here, hmm. Oh, okay. Let's see. If I remove exactly 1 point at the end in the square, then what? Then we'll try to go. Hmm. I'm not sure. Maybe it is. So if this also ends up having the least upper bound property, I can't prove it. So yeah, I am struggling to find a counterexample. So that's something at least. But yeah, this one definitely doesn't have the property. All right, then yeah, let's try to attempt push section 4 now.